Welcome to our AP Physics 2 presentation on nuclear physics. We're going to start our discussion of nuclear physics by reviewing what you should already know from your chemistry classes on the structure of the nucleus, including the forces that hold it together. An atomic nucleus consists of protons and neutrons. Protons are, of course, positively charged, and neutrons have no electric charge. It is the number of protons that primarily determines how an atom behaves chemically, because the number of protons will determine how many electrons a neutral atom of the element will have. And it is those electrons that are involved in the chemical reactions. Now here we're going to be more concerned with the nuclear reactions, so we're going to need to concern ourselves with both how many protons and neutrons we have. So we identify the chemical element by how many protons it has, and then the specific number of neutrons that it has will determine what isotope of the atom we're dealing with. So different isotopes of an atom can have different number of neutrons for the same number of protons, which is what determines what element we have. For historical reasons, the letter A is used to designate the sum of the number of protons plus the number of neutrons, because that is equal to the approximate atomic mass. Protons and neutrons each have an atomic mass of essentially 1. We'll talk more about that in a later section. And so the atoms, before we realized that there was protons and neutrons, the atoms were identified by their mass. So when they discovered that there is a separate number of protons, that was given the letter Z. Z is referring to then the atomic number, which is the number of protons, and then N is the number of neutrons. So the atomic mass number is just the number of nucleons, which is the number of protons plus the number of neutrons. So one of the things we are going to continually refer to in talking about nuclear chemistry is Einstein's famous equation E is equal to mc squared. This equation is often misunderstood, but as Einstein explains it, it simply means that energy and mass are two sides of the same coin. In Einstein's equation, a given amount of mass corresponds to a given amount of energy. Let's hear Professor Einstein explain it himself.
It followed from the special theory of relativity that mass and energy are but different manifestations of the same thing, a somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal mc squared, in which energy is put equal to mass multiplied with the square of the velocity of light, showed that very small amount of mass may be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Kokra and Walton in 1932 experimentally.
Professor Einstein is a little bit hard to understand in that recording, so let me read it for you. It says, "It followed from the special theory of relativity that mass and energy are both but different manifestations of the same thing, a somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal to mc squared, in which energy is put equal to mass multiplied by the square of the velocity of light, showed that very small amounts of mass may be converted into a very large amount of energy and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Cockcroft and Walton in 1932 experimentally." In fact, this equivalence of mass and energy leads to the fact that in nuclear physics we often will use units of mass and units of energy interchangeably in describing the mass or energy of a fundamental particle. First, let's talk about the units of mass that they use. Because it's difficult to talk about very, very small amounts of mass in kilograms, they use another unit, which is the atomic mass unit, or U. So 1 U is 1.66 times 10 to the minus 27 kilograms, meaning that each of the fundamental particles you see here have their mass equivalents in U. For example, a proton is just a little bit over 1 U. A neutron is a little bit more than that. An electron is about 1/2000th the mass of a proton. But as I said, in nuclear physics, mass and energy are equivalent. So very often, instead of giving a mass, they will talk about a particle in terms of its energy. Usually those energies will not be given in joules, they'll be given in electron volts. You recall when we talked about photoelectric effect, the electron volt was the energy of a 1 electron charge moving through a potential difference of 1 volt. That's its change in potential energy. But since mass and energy are equivalent, you can say masses in terms of energies. For example, a proton, which has a mass of 1.007276 U's, has a energy of 938.3 mega electron volts, and those two measures are entirely interchangeable. Now we know that protons both all have a positive charge, and so therefore, if you were to bring protons together to try to form a nucleus out of them, if you were relying on the electric force, you wouldn't be able to do it because the protons would repel each other, and the neutrons wouldn't be of much help because the neutrons having no charge, they're not going to help your protons attract each other. However, if you can get the protons to be within a certain distance of each other, and it's a very, very, very small distance, there is another force that is stronger than the repulsion experienced by the electric force, and that is called the strong force sometimes because it's stronger than the electric force, and it can overcome that repulsion and it eventually turns to an attraction. And both neutrons and protons attract each other by the strong nuclear force. Now, we've talked a lot in this course about the difference between a system and an object. And we have said that an object is something that has no internal structure, or at least we can consider it to have no internal structure for the purposes of what we're doing. But it's really difficult to talk about something that has no internal structure in reality. Protons and neutrons, for example, would have to be considered to be systems ultimately because they do indeed have internal structure. Protons and neutrons are made up of 3 quarks, and those quarks are held together by the strong force. We have never been able to observe quarks independently. Problem is, when you try to break a proton up into its constituent particles, well, you have to add energy to pull things apart that are attracted to each other. And when you add energy, you tend to make new particles. So instead of getting the quarks to split up, you just get new quarks. Now, quarks, as far as we know, though, have no internal structure, and so they really could be considered to be the ultimate objects, along with electrons. Photons and neutrinos, too, as far as we know, have no internal structure, and so they are considered to be the true objects, I suppose. They also have no size, as far as we can determine, electrons and photons and neutrinos, certainly. So it's not like they can do things like rotate or other things that classical particles could do. This would be a good chance for us to review all the fundamental forces then that we know about. We have the strong nuclear force, the electromagnetic force, the weak nuclear force, and gravity. Now, we're going to rank the strengths of these forces. It's sometimes difficult to rank the strength because you have to consider what particles we're talking about, what kind of interactions are we talking about here. And so this is just an approximate guide. The electromagnetic force and the weak nuclear force, it turns out they are just different aspects of the same force. At low energies, they appear distinct, but at higher energies, they end up being the same. So if the strong nuclear force were given a strength rating of 1, let us say, and its range is about 1 femtometer, which is 10 to the minus 15 meters, and the particle that mediates that force, that is to say the particle that's exchanged between two things that are attracted by the strong nuclear force, is called the gluon. And then the electromagnetic force, then, under certain circumstances, would be considered to be about 1/100th the strength of the strong nuclear force. And as far as you know, its range is infinite. It does decrease as the inverse square of the distance away. But as far as you know, its range is infinite. In fact, we have seen light coming to us from stars that are billions of light years away from us. And so therefore we know that the electromagnetic force must at least travel over that distance. And the particle that caused the electromagnetic force is the photon, as you might recall. The weak nuclear force is generally considered to be weaker than even the electromagnetic force. It too has a limited range. It is less than 10 to the minus 3 femtometers, and its particles that mediate it are called intermediate vector bosons. There's 3 of them listed there. And then, of course, the force of gravity, which is kind of the odd force out here, if you will, because we don't know how to link the force of gravity with the other 3 forces. There are various ways of linking the weak nuclear force and electromagnetic force are the same force, and then you can link them together with the strong force using theories of fundamental physics. But linking gravity in there has proved to be very difficult to do.